think actually some of this stuff you guys will probably remember maybe from Algebra 1, maybe even from middle school doing some of this kind of stuff. But we're going to give some formal definitions to 3 different types of probability. So we're going to do theoretical, experimental, and then just a really short example on geometric probability. But before we get into that, I just have a couple definitions for you guys up here at the top. So just an event. It just says the event is the set of all outcomes you are looking for. So, for example, like if we'll do this in a second, but if I flip a coin and I say I want to get heads, the event I'm looking for is me flipping a coin and getting heads. Or if I want to say flipping a coin and getting tails, the event would be getting tails if that's what I'm looking for. Now, the sample space is actually the set of all the possible things that could happen. And again, we're going to talk about this in a second, but if I was flipping a coin, sample space, like I could either get heads or tails as long as I have a fair coin. Those would be the only 2 things that could happen. That would be my sample space. Now, those 2 things are used to calculate probabilities. So probability in general just measures the likelihood of the event you want to happen occurring. And probability of an event is always between 0 and 1. Now, you can write these as a decimal, you can write these as a fraction, or if you want to, you can also write these as a percent. You could do like 0% to 100%. The 0 would correspond to 0%, the 1 would correspond to 100%. Now, right underneath this here, it says an impossible event has a probability of 0. So something that can't happen. So I'm trying to think of a little example. Like if I flip a coin, I'm only going to get heads or tails. So if I flip a coin and I say, what's the probability I roll a 1 on a die? That's not going to happen because I'm flipping a coin. So it's probability, if it can't happen, it's 0. If an event is certain to happen, like it has to happen, probability would be 1 or 100%. So if let's say example of that, if I flip a coin, probability heads or tails, well, it has to be one or the other, so that would be 100% probability, just as a little example. And forgive, for some reason, I copied those little definitions that are right there above that, so just cross that out. Okay. Now, I'm going to write a fraction here, we're going to work on theoretical probability first. So theoretical probability is what should happen in theory. Like this is what we think should happen if we were to do something. Okay, so this is the number of outcomes in the event that you want to happen divided by number of outcomes in the sample space, which we're going to work on some examples right underneath here. But that's what's going to give you your fraction or your decimal, or we can convert those to a percent. So number of outcomes in the event divided by the number of outcomes you have in your sample space. So that's all the possible things that can happen. So we were just kind of talking about flipping a coin just briefly. So flipping a coin, the sample space would be heads or tails. There's only 2 things that can happen just a normal coin, nothing weird, okay? So if I flip a coin, there's only 2 things that can happen. I can flip up heads or I can flip up tails. Now, if you see what I've got to the side, if you've got, like I have P and then in parentheses heads. If you have this and there'll be something in the parentheses, that means probability of whatever's in the parentheses happening. So if you see, like I have there P and then in parentheses heads, that means what's the probability if I flip a coin I get heads? Okay, so if I flip a coin, one side of the coin is heads, one is tails. So the number of ways I could get heads would just be 1 out of my sample space, which is 2. So probability of me flipping heads would be 1/2. All right. Now, as a lovely decimal, 0.5, right? Or if you want to write that as a percentage, 50%. Any of those answers are acceptable. So if you want to do the decimal, if you want to do the fraction, if you want to do the percent, whatever makes more sense to you is fine with me. Also, if you flip a coin, the probability that I flip tails is exactly the same. So my event would be that I flip tails. There's one way that can happen out of the two possibilities for my coin. So that would be the same thing, 1/2, 0.5, or 50%. Any of those answers are options. Okay, now I'll just ask you guys if you can help me out with this one. So roll a die, like a normal dice, like 6-sided used in a board game kind of thing. If I just roll a normal 6-sided, sometimes they call it a number cube, what would be my possible samples, or what are all my possible outcomes? Like if you just roll a die, what could happen if I roll a die? Right, okay, so what are they? Exactly, so there's your sample space. 1, 2, 3, 4, 5, 6. All right. So there's 6 possibilities in my sample space. I wrote out all 6. What's the probability if I just rolled a die that I got a 1? 1 out of 6, done. Okay. Now, what is the probability I roll a die and then this says not 6? So basically, anything but, yep, 5 out of 6. Anything but 6 would be 5 out of 6.
3 out of 6.
Okay, he's working ahead. All right. So probability odd numbers that you can roll on a die, just so you guys know, would be like the 1, 3, 5. So out of all the possible outcomes, 3 of them would be odd numbers out of 6. And then if you guys can, try and reduce a fraction if you can. So that would actually reduce to 1/2 for my probability. And again, you can write these decimal, fraction, percent, whatever you like better. 1/6. This is 0.16 repeating, which would be 16.6 repeating percent. This guy is 0.83 repeating, which would be 83.3 repeating as a percent. And then the 1/2 would be 50%, like we did with the heads. Some of these are weird decimals, so if you want to use the fraction, completely fine, or if you want to use the decimal, or if you want to use the percent, any of them are fine with me. Okay, now, 2 more examples are kind of split down the center here. This one is a little bit related to what we were talking about yesterday. So this says I have 3 true-false questions, and I'm just going to answer them at random. So just true or false for each of the 3 questions. So I'm going to have you think about what we were doing yesterday with that fundamental counting principle or multiplication counting principle. So if I have 3 questions, right? And so for my first question, I can answer true or false. Okay? So for my first question, 2 possible ways I could answer it. We could either pick true or false. I'm going to try and use this to figure out the total number of possible outcomes we could have here for our sample space. So just real quick. So for the second question, same thing. I could pick true or false. For the third question, I could pick, I don't know why I just wrote a 3, true or false, so 2. So if I multiply those all together, that should give me the total number of possible ways I could answer 3 questions randomly on a true or false question. So it'd be 2 times 2, which is 4, times 2 again. So there should be 8 possible outcomes. It does say to go ahead and write out the sample space. So these don't have to come in any particular order, but I'm just going to try my best to write all the possible ways I could answer 3 true or false questions. So like we could do, let's say we did all 3, we just guessed true for all 3. And then I'm just going to mix these up so they're each different. All right, so I could do, let's say I did true, true, false. I could do true, false, true. I could do true, false, false. So those are all the possibilities with the first question being true. And then anything that we could think of from there. There should be 8 total that we can write down. All right, so let's say I answered the first question false. So I could actually answer all 3 of them false. I could do false, false, true. I could do false, true, false. And then the last one, I could do false, true, true. Those are all the possible ways that if I just randomly guess on 3 true, false questions, there's 8 possible ways I could do that. Okay, now underneath that it says, what's the probability, if I do this at random, like you get a pop quiz or something and you do this, what's the probability that you would get them all right? 1/8, right? Okay, so only one of these could be all right, right? They're all different, so only one of them could be like the answer key, if you will. I don't know which one it would be, but you would only have one out of the total 8. And let me see what that is as a decimal. It's not huge. 7 divided by 8. Okay, this is 0.125, or this would be a 12.5% chance that you would guess all of them right if you just did that randomly. Okay, now forgive, I should have printed this in color because it looks terrible, but this is supposed to be like a little spinner, like for a board game. So the sample space over here, if you guys can read, I'm really sorry, they have letters on them. So the R, this is supposed to be red, the O is supposed to be orange, the Y is supposed to be yellow, bless you, G is supposed to be green, bless you, B is supposed to be blue, and the P is supposed to be purple. So the sample space there would be the 6 colors that are on the spinner. Okay, now on that, those are all equally spaced. They're all equally the same exact size. And what would be the probability there that if I just randomly spun this, that it would land on red? 1 out of 6, right? There's six equal things. All the colors are the same size in terms of the area they cover, so just 1 out of 6. Okay, what would be the probability I would land on either blue or yellow? 2 6. Good deal. And then if you want to reduce that, that is 1/3. What is the probability I spin the spinner and land on white? 0, because there's no white space on there, even though it kind of looks like that on my copy. All of those are supposed to be a color, but the probabilities there is 0 because it's not possible. There's no white space on that spinner. So that would be probability of 0. Is anybody having a question about the theoretical probability? Okay, I'm going to give you definition of experimental probability here on the bottom, and then we'll flip over and actually do an example. So experimental probability, you either have to oh my goodness, I can spell. You either have to perform a set of trials, or, which our example in the back will be like this, have data given to you of somebody else performing an experiment or a trial. So you have to have trials, or you have to have data given to you about somebody else performing an experiment or a trial of some kind. So like if I mean a trial, like let's say I took a coin, I flipped a coin 10 times, and I got heads 6 times, and I got tails 4 times. Then the experimental probability, how you would actually figure it out, is number of times your event occurred in the trials. Thank you. Good morning. And then divided by the number of times. So like I was saying, if I flipped a coin 10 times, and I got heads 6 times and tails 4 times, my experimental probability of heads would be 6 out of 10, and my experimental probability of tails would be 4 out of 10. It's based on the trials, not the theoretical, what you think should happen. So we either need to actually perform trials, which we're not going to do on this lesson right now, but they can also give you data, and you can use the data to do an experimental probability. Okay, so that's what we're going to do on the back. So I'm going to give you the data. So this is like our experiment, basically. So it says the teacher collects a survey that asks for the eye color of each of his students. Okay, so the experiment is basically like, what's your eye color? And we're going to ask that of all the students this guy has in his classes. So here's the results. You got 12 people with blue eyes, 58 with green, 58 with brown, 2 with green, and 8 with hazel. So first thing I would probably recommend in that situation, figure out how many total people this dude has in his classes. So I would just take literally just 12, 58, 2, and 8, add those guys up. this should give you 80. So that would be essentially your number of trials. There's 80 people that we asked this question to, and these are the results. Okay, so the experimental probability, if I randomly select one of these people out of this group of students, and the probability they would have blue eyes is just what I have literally in the table. So this would be 12 out of 80. And then if you guys want to do, like, let me write that as a decimal. I think it's 0.15. I'm just going to check real quick. Yes. So this is 0.15 or 15% of the students in this guy's classes. That's the experimental probability that you would have blue eyes. So for brown would be the same thing. You just grab from the table. There's 58 out of the total 80 people that got asked what color their eyes were. And as a decimal, if you want to do that, this is 0.725. So this would be about 72.5%. So lots of people, and that's pretty normal. Lots of people have brown eyes because it's a dominant color. Now, green is a little bit more rare here. You only have 2 people out of 80 that have green eyes, which is a super tiny percentage. So if you do this as a decimal on your calculator, you get 0.025. Now, remember, if you do like to do the percent, you're going to scooch that decimal place over 2 spots. So this is only about 2.5% of the people in this class would have green eyes. And then Hazel, again, I'm just grabbing this data from the table. Out of the 80 people, we asked them their eye color, 8 of them. So it'd be 8 out of 80. This is 0.1, or just about 10% of the people. So we're just basing it either on the data, or in this case, we have data, so we didn't do trials. So you would either do trials or you would base on data that you're given. Okay, now, probability. If I randomly pick somebody out of this group of students that they have blue or green eyes, all you have to do is take those 2 colors and add them together. So 12 people have blue eyes and 2 people have green eyes out of the total 80. So it'd be 14 out of 80 if I randomly selected somebody from this group. And this is going to give you 0.175 or 17.5 as a percent. Okay, so this is probability of not, so I don't want them to have green or hazel eyes. So if they don't have green or hazel, then they're going to have blue or brown. So these 2 would be equivalent in that situation. So if I say I don't want them to have green or hazel, that would be equivalent to me saying the probability they have blue or brown. So there's a couple ways you could do this. You can add these 2 guys together, the blue and the brown. You do 12 plus 58, and you'd get 70 there out of 80. Or if you want to do the not version, there are 2 people with green eyes and there are 8 people with hazel eyes. So I could take the total, which was 80, and I don't want these people involved, so I could subtract the 2 and the 8, so that would be subtracting 10. Either way, you're going to get 70 out of 80. So there's a couple ways you could do that problem. So this is a much larger percentage. 0.875 or 87.5%. Does anybody have any question? Okay, I'm going to do this a teeny tiny bit out of order. So the example I have at the very bottom of the page is actually not a geometric probability, it's actually an experimental probability. So I'm going to have us look at this bottom example, and then I'll go back and do the geometric probability. So this Venn diagram, this is actually an experimental probability, like a way you can display it. So you guys may have seen something like this before. But it says all the members of club were asked if they eat apples, that's the A here, or bananas, that's the B. And the results are displayed in the Venn diagram. Okay, so I just want to go through and see if you guys know how to read this. Like, what do these different numbers in this diagram mean? So if I look at the 17, what does the 17 in that diagram represent? These are all representing people. So what would the 17 be? Only apples, right? These people only eat apples. What is the 52 It's in kind of in the middle there. What is the 52? Both. So all these people in the middle here, they eat both apples and bananas. The 20 would be just like, okay, like the 17, just bananas. Okay, so the 20 would be just bananas. What is this, like 41 that's not in the circles? Neither. Good. Okay, so this, if you're not involved in the Venn diagram, but it's still in the picture, that means there's 41 people in this club that don't eat either one. Okay, so this is still experimental probability. Now, how would you take that Venn diagram to figure out how many total people are in the club? Add them all together. Okay, just don't add the 52 twice. You're just going to do, like, we've got 17 that eat apples only, 52 that eat apples and bananas, 20 people that only eat bananas, and 41, they don't eat either one. So you got 130 total people in this group. Okay, now, experimental probability here, based on the people in this club. If I pick somebody at random out of this group, what is the probability that they would eat apples and bananas? Like, how could I set up a fraction to figure that out? Perfect. This would be 52 out of 130. I'm just going to grab my calculator real quick and see what that is as a decimal. So, actually, this is a nice decimal. I got 0.4, so it would be 40%. Now, a little bit trickier. What's the probability I pick somebody at random out of this club and they eat bananas? How would you figure out, just randomly pick somebody out of this group that they would eat bananas? Yes, how'd you get 72? Sweet. So the 52, they eat bananas. These 20 also eat bananas. These eat both, but they do eat bananas. So you just add those two together. So to get the 72, we're taking the 52 plus the 20, and that'll give you 72 out of 130. Let me see what that is. I got a long, nasty decimal. It's about 0.55. I'm rounding that a little bit, or about 55%. So that's also another way to display your experimental probability. Okay, does anybody have a question about experimental probability? Okay. Let me scooch back. We'll do one more today. This is geometric probability. Okay, geometric probability, we're going to do a little throwback to geometry. So you're going to have to find probably an area of some kind when you do a question that involves this. So geometric probability is calculated. You find the area of the event that you want to happen. We're going to do a little thing with a dartboard to illustrate this. And you're going to divide that by the total area. So area of what you want to happen divided by the total area to calculate a geometric probability. Okay, so I've got this dartboard that's kind of displayed here. And before I do any probabilities, you have to find the total area of what you're working with. So we can have that on the bottom of our fraction when we do our probability. So I'm going to find the area of the entire dartboard. So like in the middle here, like the colored in part, this is like the bullseye. This is worth 20 points. What they're trying to label here are some distances. So the intention here is this 3 on the inside. That's the radius of that little shaded in circle. Okay, now each one of the rings here, so the next ring out you would get 10 points, the next one you would get 5 points, and then the outer ring you'd get 2 points if you land on any of these. Each one of these is the same length between where the next circle starts here. So this is 2 inches, 2 inches, 2 inches. Could anybody tell me, because I'm going to find the area of this dartboard, which is the circle, and just over here to the side, just in general area of a circle, in case you guys forget, it's just pi times the radius squared. Can anybody tell me what the radius of the entire dartboard would be? What do you think? Oh, I thought you were raising your hand. What's the radius of the entire dartboard? It's 9, yes. Okay, so like this part of it, this is 3, and then each one of these, this is 2, 2, and 2. So if I add that all up, the radius of that entire dartboard is 9. Okay, now, just for doing this today, I promise this will make it easier. I'm going to leave my area in terms of pi. So the area of the whole dartboard, pi times your radius squared. So just be pi times 9 squared. 9 squared is going to give you 81. So the area of the whole thing is 81 pi. So we'll put that on the bottom of the fraction because that's the area of the total dartboard. Okay, now the question I have first says find the probability we would randomly throw something at this dartboard and we'd land in the 20-point region. Okay, so the 20-point region is just that part in the middle that's shaded. So all I have to do is find the area of that and put that over the total area, which we just calculated there real quick. So the area of this, the radius of just this little shaded in circle is just 3. So radius of that is 3. So the area there would just be pi times 3 squared. And again, I'm just going to leave this in terms of pi, okay? So 3 squared is 9. So the area of that 20-point region would be 9 pi. Okay, so probability I randomly land on that. We're just going to take 9 pi, that's the area of what we want to happen, divided by the area of the whole thing, which is the 81 pi. And this is why I left it in terms of pi instead of estimating or something, because we could just, bless you, we can just cross those pi's right on out. They're just going to cancel out. So I get 9 over 81, which is 1/9. As a decimal, this is 0.1 repeating, so it'd be like 11.1 repeating as a percent. That would be the probability if I randomly threw a dart at this that I would land in that 20-point region. Okay, now the rest of this question is kind of tricky. So the second part just says, what's the probability I land in the 5 or the 10? Okay, so the 5 and the 10 are the two rings here that immediately follow that bullseye. So what is the probability? I'm just going to try and shade this. You guys can see why I did not teach elementary school because I can't color very well. Whatever. In here would be the area. Just this yellow part though, not the bullseye. I want to find the probability I would land on that poorly colored yellow part. How would I figure out the area of that yellow part? So this is kind of tricky. How would you find the area of just what I have shaded in yellow? Anybody, this would be throwback to geometry. Any idea how you might find the area of just that yellow part that I just kind of colored with my highlighter?
Separate the equations and then add them.
What do you mean by?
Like do 5 first, and then find the area of that, and then 10.
We could do it like that. It might be a little. What were you thinking?
You just do pi then put 4 as the radius.
Okay, now this is what we were running on last period. This is tricky. Okay. If I did the radius there, is the radius of that 4? Because does that go all the way to the center? This is really weird. Okay, see if this makes sense to you guys. If I would, let me just pretend the bullseye was filled in. I know this is super weird. If I pretend the bullseye was filled in, I could find the area of that whole thing, like the yellow part and the bullseye. But I could go back and subtract the bullseye out, and that would just leave me with the yellow part. Does that make sense? Okay, so here's what I would do. Okay, so just ignore this outer ring because we're not worried about the 2-point part. If I did this whole circle here, pretend the bullseye was part of that. The radius, you'd have 3, 2, and 2. So the radius of that would be 7. Okay, so if I do pi times 7 squared, that would be the area of the yellow part I colored and the bullseye. But I don't want the bullseye as part of my area, so I'm just going to subtract that out. So we just did that in the last question. That was the pi times 3 squared. So I'm going to leave this in terms of pi. It'll make it easier to work with. 49 pi would be those two yellow rings that I colored and the bullseye together, and I want to subtract out the bullseye, so I only get the yellow part. This would be 9 pi. This is like doing 49x minus 9x. Those are like terms. So the area of just the yellow part would be 40 pi. And then once we're there, that's the area of what we want. So I'm just going to do 40 pi over 81 pi. Pi's cancel out. And 40 over 81 doesn't reduce, but let me see what it is as a decimal here. So this is about 0.49 or about 49%. So that's really tricky to do that. But all I'm doing is I'm just subtracting the bullseye out, and the leftover has to be that part that I just shaded in yellow. Does anybody have a question? Okay, the homework for this evening is actually on paper, so it should be in your lovely little homework packet. And